Morning, this is A.B.Krishna. Today topic is coordination compounds. I'm starting coordination compounds. Most important topic for all types of examinations. Coordination compounds, compulsory one question, whatever the type of examination it is, mains or advanced or NEET or whatever the type, private university examinations or national wide examinations, one question, it is damn sure, from theories, from nomenclature or from isomerism or applications, anyone, from any topic, from this lesson, one question will come compulsory. So let me start. What are the coordination compounds? How we have to give the names? What is isomerism? What are the theories explaining the structure of coordination compounds? Everything let me see now. Let's start. Coordination compounds. These are one type of complex compounds. One type of complex compounds. Actually, complex compounds are two types. Complex compounds are two types. The first type is called double salts. These are also complex in nature. Another one is coordination compounds. First one is double salts, second one is coordination compounds. What is the difference between double salt and coordination compounds? Let me see now. First, how we got this term, coordination compounds, coordination chemistry, how this has been arised. Simple concept, everybody know about transition elements. We can also call them as the block elements. Transition elements have the tendency to form complex compounds by coordinate covalent bond. The transition elements have the tendency to form complex compounds by coordinate covalent bond. We can also call that as dative bond. From this concept, the word and the concept coordination compounds and the study of that coordination compounds as coordination chemistry have been arised. So why we are calling them as complex compounds means the structure is complex. It has been formed by mixture of two or more simple compounds. That's why we call it as complex compounds. Like that, another complex compounds also there. They are called double salts. These are complex compounds. Coordination compounds also called complex compounds. So why they have been divided into two types? What is the concept to divide the complex compound into double salts and coordination compounds means these are formed by just combination of simple compounds, but these are formed by dative bonds. Dative bond. We can also call them as what? Coordinate covalent bonds. The coordination compounds and double salts are differed by one thing, that is dative bonds are present in coordination compounds. There are no dative bonds in this. And also one more thing, these on hydrolysis or means treatment with water convert into simple constituent ions. Constituent ions means what? From which ions it has been formed, that ions will be formed on hydrolysis. Constituent ions. But coordination compounds, these on hydrolysis produce ions, but they are different from constituent ions. Produce ions, but they are differ from constituent ions means from which it has been formed, that will not be formed. Constituent ions. Let us see one example. What does that means? Suppose if I take example of carnallite. Everybody has to know some complex compounds names. In that one complex compound is, that is double salt, is carnallite. The formula of carnallite is KCl MgCl2 6H2O. This is a double salt, a complex compound formed by combination of three compounds, KCl, MgCl2 and 6 water molecules. So this is called carnallite. In solid state it is stable. In solid state this double salt and this carnallite is stable, but on hydrolysis this compound gives, this compound gives, I write here, K plus Mg2 plus and Cl minus ions tests. The test which have the K plus and Mg2 plus Cl minus ions, these solutions, the double salt solution, the carnallite solution, will give the test of these ions. The carnallite in solid state, it is stable. It is different compound, does not have the KCl properties, MgCl2 properties. But on hydrolysis, it produces the ions from which it has been formed, and it gives the test of potassium, magnesium and chlorine. Means converting to its constituent ions on hydrolysis. That is called double salt. And coming to coordination compounds. These do not form a constituent ions from which it has been formed. They produce different ions. Example, if I take one example, K4 Fe Cn 6 times, if you take, it is an example of coordination compound which on hydrolysis, when we add water to this, it dissociates into 4K plus Fe Cn 6 times 4 minus will be formed. So based on this concept, it has to give the test of K plus, Fe2 plus and Cn minus ions test. It should give these tests, but this complex will not give these tests. The solution of this complex, the solution of this compound will not give the test of potassium, iron and cyanide. It gives the test of potassium and this complex anion tests. So like this, it produces different ions as compared to constituent ions from which it has been formed. Like that, double salts and coordination compounds have been differentiated. So this is the basic difference between double salt and coordination. Both are complex compounds. But this on hydrolysis, both are stable in solid state. Double salt and coordination compounds both are stable in solid state. We can differentiate them on hydrolysis. So if we add water to this double salt, it converts into its constituent ions and will give it's a simple ions tests on analysis. And coordination compounds on hydrolysis also produce ions, but that ions are differ as compared to its constituent ions. And one more example you can take for this double salts is alums. This is one example. Another example, second example for this is alums. All types of alums are double salts. And third example is Morse salt. Morse salt is also double salt. The formula of Morse salt is ammonium sulfate, ferrous sulfate, 6H2O. So I will write the formula Morse salt. Ammonium sulfate, NH4 taken twice, SO4, Fe, SO4, 6H2O. This is Morse salt. Alums. Alums means there are the complex compounds which have the a formula that is M2SO4 or M2SO4 taken 24H2 like that is the best example is potash alum. If I take one example is potash alum formula K2SO4 dot Al2SO4 taken twice dot 24H2O. This is one of the example of alum. Another example for double salt. So on hydrolysis it gives ions like what? Potassium, sulfate, aluminium. It gives the test of aluminium, give the test of potassium and give the test of sulfate. But this ones, and if I write one more example for complex compounds, COCl3 6NH3 if I take, this is also complex compounds. On hydrolysis it gives CONH3 6 plus complex cation and Cl anion. Cl minus chloride anion will give different ions. But actually it has been formed from CO3 plus Cl minus and ammonia. It has to give that one, but it will not give because it forms the cobalt is transition element. It forming a dative bonds and forming coordination compounds like that. The complex compounds are two types based on their test on aqueous solutions. And once again, these coordination compounds are further two types. Let me discuss that one. Have you got the idea? Complex compounds. Coordination compounds are one type of complex compounds. Actually, complex compounds are two types: double salts and coordination compounds. They are being separated based on the tests of their constituent ions on hydrolysis. In solid state, both are stable, but on hydrolysis they will give different things. Double salts will give like this, and coordination compounds will give like this. Alright, let me come to coordination compounds. Once again, coordination compounds are two types. I'll write that one also. Please listen. And better, if you can write the notes what I am writing on the board, that will be more helpful for you for competitive examinations. One thing I am saying, I am taking these videos for those students and those persons who cannot attend the classes by some reasons. Somebody cannot attend the classes because of health problems and all that things. Actually, I got inspiration and I got an idea to take the video classes by one student. I know he has suffered some health problems, means injury. He has been accidentally got some injury for the leg. He has not attended, but brilliant student. He has not attended the classes. He faced a lot of problems for practicing. So for him, I started the class. By thinking about him, I started. Those who cannot attend the classes, they can easily learn the chemistry and they can learn the topics, how they are getting the subject in the classroom. So please listen carefully, and if you can, write down what I am writing on the board. Right. Next, coordination compounds. In complex compounds, I separated double salts and coordination compounds. In these coordination compounds, once again we have coordination compounds. These are once again two types. One is perfect complexes. Perfect complexes. Second one, imperfect complexes. Coordination compounds in itself, these are two types: perfect complexes, imperfect complexes. Perfect complexes means what? These complex ions. On hydrolysis we got complex ions, no? So coordination compounds on hydrolysis giving complex ions. That may be cation or anion. The complex anion will not dissociate further. These complex ions may be cation or anion. These complex ions, maybe cation or anion, do not dissociate further. Do not dissociate further. They are stable. At any cost, they do not dissociate. Therefore, stable. Example, I will explain with the example. Same, initially I took this one up. So K4, Fe, CN6, that one only I am taking. Post on hydrolysis, it gives 4K plus Fe, Cn 6 times 4 minus anion. This anion is complex. This on further do not undergo hydrolysis. Means it will not give the test of iron and cyanide. But it will give the ions of K plus and complex. They are called what? Perfect complexes. Imperfect complexes means what? These complexes forms either cation complex or anion complex, but that complex cation may undergo further dissociation. That's why we call it as what? Imperfect. These complex ions, no doubt that complex ion is formed by D2 bonds, coordinate covalent bonds, but they are further converted into ions. These complex ions dissociate into further ions. Dissociate into further ions. I will take one example. The example for this is K2 CD Cn 4 times. If you take, first it dissociate into 2K plus CD Cn 4 times 2 minus. But here it is imperfect crystal, imperfect complex, so it further dissociate into CD2 plus 4Cn minus. Don't get the confusion from imperfect complexes and double salts. Double salts also converting into simple constituent ions. Here also imperfect complexes converting into simple constituent ions. But the difference between them is double salts do not have the D2 bonds, but imperfect complexes, they have the D2 bonds. So cyanide is the ligand forming D2 bonds with cadmium, forming complex anion. But this is not stable, further converting into that. That's why we are calling it as imperfect crystal, not double salt. It is not double salt. It is imperfect coordination compound. But here it is perfect coordination compound. If it is not further dissociating into ions, it is called perfect complex, perfect coordination compound. If it is converting into simple ions and further after formation of D2 bonds also, they are called imperfect crystals like that. Coordination compounds are important types. First, complex compounds 2 types. Double salts coordination compounds. Coordination compounds further 2 types. Perfect complexes, imperfect complexes. So please, if anybody has a doubt, write a comment, and if any improvement you want further in this video classes, please suggest me. I'll improve myself to give the best, the better concept on the subject. So I'm trying my level best. If you want further, please suggest me. I will explain in detail. Okay, thank you. Next topic in this is the types of complexes, types of all these things we have seen. And if you want, you can check further examples also. In that examples, if anybody has a get to the problem, please write down the comment and write down that example. I will explain further if you want. If you want, I'll write, and even I will solve that problem. If any problem you have, write down that as a comment, and I will post the solution as the photocopy to you. Okay. Alright. Next, the terms used in coordination compounds. Terms used in coordination compounds. Here some simple terms are there, most of the students know. Some different, difficult, means some typical terms are there. You have to concentrate on that. The first one, so the first term is complex ion. Complex ion. The simple concept. What is complex ion? Complex ion means what? It is the ion formed by ligands and central metal ion by dative bonds. The ion formed by ligands and central metal ion by dative bonds. Dative bonds means what? Coordinate covalent bonds. They are called complex ion. I'll take one example. I'll write that example here. That example is, suppose if I take CO NH3 6 3 plus 3 Cl minus. This is complex ion. This is called complex ion. It has been formed by ammonia ligand, 6 ammonia ligands and cobalt central metal ion. It has a charge. It is cation. Complex cation. So complex ion means an ion is formed by combination of central metal ion and ligands by dative bonds. That is complex ion. Second term is coordination number. Coordination number. Simple. Number of dative bonds present around the central atom is called coordination number. Once again I am saying number of dative bonds. Number of dative bonds present around central metal ion. Around central metal ion in complex ion. They are called coordination number. Number of dative bonds, number of coordinate covalent bonds. So in this example, 6 ammonias forming 6 dative bonds with cobalt. So coordination number of cobalt in this complex is 6. Simple point, very easy to remember. The number of coordinate covalent bonds, the number of dative bonds present around the central metal atom, which that bonds have been formed by donation of electron pairs from the ligands. So they are called coordination number. Here in this complex, the coordination number is 6. The reason, 6 ammonia molecules giving 6 electron pairs to the cobalt and forming 6 dative bonds. So that is called coordination number. After that, number 3, coordination entity. Coordination entity. In some books it is there as coordination sphere. Coordination entity, coordination sphere. So this is next term. So what is that? Let me explain with that example. Coordination entity and coordination sphere means the space where the dative bonds are present around the central metal atom by ligands is called coordination sphere. This area, this thing is called coordination sphere. Coordination sphere. This area. And this is called central metal ion. Central metal ion. And these are called ligands. What are the ligands? Let me discuss later. First, this central metal ion. This area total is called coordination sphere, and this area is called ionic sphere, because here ionizable ions are present. Here non-ionizable things are present. That's why coordination sphere. That is called coordination sphere. The area or the space around the central atom where the ligands are attached, linked to the central metal ion by dative bonds is called coordination sphere. Ionization sphere, we can also call it as ionic sphere. The sphere, the space where ionizable ions are present in the complex, that is called ionic sphere. Next term is ionic sphere or ionization sphere. Ionization sphere. Ionization sphere means what? The space or the area where in the complex ionizable ions are present. 3 Cl minus is there, na? They are called ionizable ions. At that place, that space at Cl minus is called what? Ionization sphere. So coordination sphere, ionization sphere, coordination number, complex compounds. After that, next, oxidation state is important. So please see how to calculate oxidation state and what is oxidation state. Let me see now. Oxidation state means what? Next term, fourth na. Next coming to fifth. Oxidation state. Oxidation state of central metal ion. Of central metal ion. Suppose if I take that one, CO NH3 6 3 plus, if it is there. This 3 plus is not the oxidation state of this cobalt. Of course, sometimes may be same or different, but here, whatever the charge is present on the complex is not the oxidation state, it is a charge of ion. Suppose, another example if I take FeCN6 4 minus, if it is there. This is not the oxidation state of iron. This is charge of ion. Same thing, this is not oxidation state of cobalt. This is charge of ion. So how we have to calculate oxidation state of central metal ion? Please see. For anything, if you don't know oxidation state calculation, please see, this is the formula you have to follow. Oxidation state equal to, if you want to calculate oxidation state of cobalt, consider it as X, because we don't know. That's why I am writing it as X, plus how many ligands are there? 6 ligands. And ammonia is neutral ligand, means no charge. If the ligand is neutral, no charge. If the ligand is negative, that charge, whatever, for example, minus 1 is there, we have to take minus 1. If it is minus 2 is there, we have to take minus 2. Here, the ammonia is neutral, so charge is 0. Less, nothing is there. After that, whatever the charge is present, that we have to write here. So then, what is happening here? X plus 6 into 0 means 0, so X equal to 0 plus 3. So cobalt oxidation state in this case is what? Plus 3. That's why I told you sometimes may be same, but this is not oxidation state. Here we got, no problem. Let us see that example. That's why I wrote second example to get idea, because here you will get a confusion, because same oxidation state is there, charge is there, na? So you will get a confusion. That's why I have taken another example. So here we got CO plus 3 oxidation state for cobalt. Coming to next, here iron. In this case, how we have to calculate oxidation state? Once again I am writing, we don't know oxidation state of iron, so let me write it as what? X plus, how many cyanides are there? 6. Cn minus will be there always, means what? Charge of ligand here is what? Minus 1. Equal to, after that nothing is there, so minus 4. Like whatever the charge is there, we have to write equal to as that. So X equal to X plus 6 into minus 1 equal to minus 4. Then what will happen? 6 X minus 6 equal to minus 4, X equal to plus 2. So here iron oxidation state is what? Plus 2, not minus 4. Plus 2, not minus 4. You have to calculate like this. You have to calculate like this. So not only this charge, if charge is not there, if the complex is there, there also we can calculate oxidation state. Please see. Let me take an example. Right. Cr NH3 4 Cl2 Cl is there. If he is asking to calculate oxidation state, so very simple. Once again, how to calculate oxidation state? Listen everybody. Oxidation state equal to, we have to calculate oxidation state of chromium. So let me consider as X plus, once again I told you, ammonia is what? Neutral ligand. There are 4 into 0 because neutral, no charge, plus 2 more chlorines are there in the coordination sphere, coordination entity. So 2. Chlorine always exists as what mass? Cl minus, means minus 1 charge will be there on each chlorine, plus, after that also we have done, so plus 1 into minus 1 equal to 0. The total complex doesn't have any charge. That's why I wrote it as what? 0. Including, I included here also because after 2 chlorines it is there in coordination entity, that's why I wrote separate. It is there in ionization sphere, so I wrote separate. 1 chlorine is there. So then after that, if I write X plus 4 into 0, 0 plus 2 into minus 1, so minus 2 minus 1 equal to 0. So total X minus 3 equal to 0, X equal to plus 3. So chromium oxidation state here is what? Plus 3. Like this also you can calculate. If it is neutral, even complex is neutral, you can calculate like this. If ion is there, you can calculate like this. For cation complex, oxidation state calculation. For anion complex, oxidation state calculation. For neutral complex, oxidation state calculation is there like this. You can calculate oxidation state. Very easy, simple. Don't be confused. Don't be get excited if you are not getting the answer. If you are getting excitation, next question impact will be there. So please be calm and be serious on the concept. Easily you will get the concept. That's why how to calculate oxidation state of simple metal ion I wrote. This is the formula, simple universal formula to calculate oxidation state. For cation complex, this is the way to calculate oxidation state. For anion complex, this is oxidation state calculation. For neutral complex, this is oxidation state calculation. Like that, we can calculate oxidation state for central metal ion in the complex. Got it? After that, charge of the oxidation state completed now. Shall I remove? Alright. Next, charge of the ion. Charge of the ion. What is the charge of the ion? Like that. Let us see now. Next, after that, 6th one is charge of ion. Charge of ion. How we have to calculate charge on the ion? Suppose he has given 3 complexes. He has given 3 complexes. Let me take CO, Cl3, 6NH3, 1 complex is there. CO, Cl3, 5NH3 complex is there. CO, Cl3, 4NH3 complex is there. CO, Cl3, 3NH3 complex is there. So in these complexes, he may ask the question like this: what are the charges? What are the charges on complex ions? Whether it is cation or anion complex, what are the charges on complex ions in these complexes or in these compounds? Like this, the question may be there. Or individually we have the charge. And you will give oxidation state. And oxidation state of cobalt is +3, like that. If you know oxidation state, you can easily calculate charge. If you know the charge, you can calculate easily oxidation state. Just previously, how we have to calculate oxidation state. Here, without both, if we are not given, he has not given oxidation state as well as charge, and asking. So at that time, you have to use your basic knowledge of D block elements. Suppose if cobalt is there, he has not given oxidation state and asking charge. At that condition, you have to think which oxidation state is stable for cobalt. Because cobalt is a D block element, as transition element, it shows many oxidation states, that is a variable oxidation state. So in that oxidation state, which oxidation state is stable, you have to know. That is different thing, but mostly 99.9%, if he is asking charge, he will give oxidation state. If he is asking oxidation state, he will give charge. Or just he will mention the molecule. You can calculate easily. So let me see now. In these molecules, how we have to calculate charge of the complex ions. So let me write it as A, it is B, it is C, it is D. So let me calculate the charges. This is very important for next topic. Awareness theory, you know, very important. Most times, if the question is coming from the coordination compounds, means he will first consider about the awareness theory. So in that theory, it is very important example. So please see how we have to calculate charge. First A, I am taking A. That is what? CO, Cl3, 6NH3. Remember one thing, coordination number of a particular metal is constant. It will not be changed. I'll explain some more things are there, but it is constant. Here, in this, what are the complex here? In all things, cobalt is common central metal ion. So its coordination number, cobalt, coordination number, cobalt, coordination number is 6. Always. For every central metal ion, certain coordination number is fixed. If you take copper, it will be 4. If you take silver, it will be 2. And if you take chromium, it will be 6. Cobalt 6, iron 6. Sometimes for copper 6 also will be there, that depending upon its geometry and complex nature, all these things. So many other things are there, but most probably I am saying, mostly I am saying. So in this case, coordination number 6, oxidation state is +3. So how we can write the complex? 6 coordination number means 6 ammonia molecules are present around it, and 3 chlorines are present outside. Means definitely its charge will be +3, 3 into -1. So like this the charge will be there. 6 ammonia, whatever the required number of ligands it requires, that ligands are present. So 6 ammonia is forming 6 dative bonds with cobalt, and 3 chlorines are present in ionization sphere, so charge will be like this. And next to B, COCl3.5NH3 is there. In this complex, how we write? Once again I am saying coordination number is fixed. It is 6 itself. But here we have only 5 ammonias. At that condition, what will happen? One of the chlorine participate in DT form. Therefore, it will present in coordination sphere like this. CONH3 5Cl. It will be there like this. Cl. So its coordination number is fixed now. So definitely 2Cl minus will be there. 2 into -1 means it will be +2. This is charge. This is charge. This is charge. Like that we make it. Okay. Next, C. COCl3.4NH3. Same thing. In this case also, how can we write? CONH3 4Cl2 Cl. Like this in mass. It is. For the fourth example, try to write that. I'll write one example. You have to say this charge of ion. FeCN 6 times X minus is there. In this case, iron oxidation state is +3. So what is charge of complex ion? What is charge of complex ion? If he is asking like this, how you calculate? It is okay. Just based on this I wrote, it is okay. But if he has given like this, he is asking what is X? X minus he has given. What is X is asking. So he has given the complex X minus iron oxidation state he has given us +3. So how we have to calculate? Have you got the idea? So How we have to calculate means already you know this one. He has given plus 3 now, so 3 plus. I am calculating the charge. Please see. He has given oxidation state of iron as plus 3, so I will tell. 6 cyanides are there, each one oxidation state charge is -1, equal to x. After that nothing is there. So then what is happening here? Equal to 3 minus 6 equal to x. So it will be x equal to what now? So here what can we write? Like this one. This is the way to calculate the charge of complex air. He has given this and he has given oxidation state and charge of complex is asking. So whatever the oxidation state he has given for this, I would like this. 6 cyanides are there, 6. Each cyanide charge is -1 and x I got. But x we got as -3. The question may be there like this. Based on the charge of complex ion. The questions will be there like this. Got it? So this is the terms used in the complex compounds, coordination compounds. How to calculate oxidation state, how to calculate charge is. These are basic points to understand the coordination compounds. Actually, it has not been started. It is introduction about the coordination compounds. Further, we have not entered. Actually, the core thing is there. Main thing is there. To understand that one, first you should know the concepts of these coordination compounds like this. How to calculate oxidation, what is the charge, what is coordination sphere, what is coordination number, what is ionization sphere. All these things you have to know. Or that you will do. Next term, 7th term is ligands. Ligands means what? Ligands means simple point electron pair donors. Generally, electron pair donors are called what? Lewis bases. So ligands are Lewis bases. Central metal ion is Lewis acid. Electron pair acceptor is Lewis acid. Electron pair donor is Lewis base. So ligands are electron pair donors. Pair, not single electron. Electron pair itself. So electron pair donors are called ligands, Lewis bases. These are 3 types based on their capabilities, based on denticity. These are different types. Ligands are several types and based on several things. Denticity, they are several types. Based on the charge, they are 3 types. Maybe neutral ligands, maybe negative ligands, maybe positive ligands. Based on the charge. Based on the denticity, there are different types. We will discuss that one later. Based on the charge and based on the lone pair electrons donation. Lone pair, because they are electron pair donors. Lone pair electrons donating and accepting. Donating or accepting tendency. Based on donating and accepting tendency, ligands are 2 types. Classical ligands, non-classical ligands. Classical ligands, non-classical ligands. So again, based on denticity, there are several types. Based on the charge, the ligands 3 types: neutral ligands, negative ligands, positive ligands. Based on lone pairs, electrons donating and accepting or not and tendency, there are 2 types: classical ligands and non-classical ligands. In this charge, these 2 are most common. Usually, ligands are maybe neutral and negative, most common. Positive ligands, rare condition will be rare. Positive charge ligand, because they have to donate electron pair with the positive charge. Positive charge means what? Lack of electrons. Still they have to donate electron pairs, so it will be there. Negative means already they have more electrons, they can easily donate. Neutral means neutral tendency, they can donate. So negative and neutral is most common, but positive is rare. Examples: nitromium ion, NO2 plus, and NS3 plus, like that it will be. Next, coming to denticity. What is denticity and what is this? Let me see now. Denticity means what? Number of electron pairs donated by a ligand is called denticity. I am writing here. Please see. Denticity means number of electron pairs donated by a ligand is called denticity. Based on that, there are different types. First one is monodentate ligands. Means it donates only single electron pair, single lone pair, one lone pair, not single. They donate one lone pair. Any ligand, if it is donating one lone pair, they are called monodentate. Bidentate, two electron pairs. Bidentate ligands means each ligand donates two electron pairs. Tridentate, please see examples. Denticity means what? Each ligand donating capacity. If a ligand donating one electron pair, it is monodentate. If a ligand donating two electron pairs, bidentate. 3 electron pairs, tridentate. 4 electron pairs, tetradentate. 5 electron pairs, pentadentate. 6 electron pairs. Single ligand can donate 6 electron pairs. That is called what? Hexadentate. Best example of hexadentate is EDTA, ethylene diamine tetraacetate. EDTA is the best example of hexadentate ligand. So that is called denticity. So most of the students know about these ligands and their structures. That's why I am not going to that one. So it is not important for competitive examinations. So if you want, please go through the books or any other things. If you are not understanding, ask me once again. I will take separate video for that, because we have to discuss separate structures for ligands. It is not the time. So now we have to concentrate on the most important things which has been there in the question paper. Which questions will come mostly. That's why I am concentrating on that. So first, classical, non-classical also it will be there. What is classical ligands and non-classical ligands? Also I will take different special ligands, all these things. I can't explain it because in this video, next video, I'll explain that classical ligands and non-classical ligands.